All right, so we want a constructive proof of the last result. So let's start by just going over what the context is. So in proving 1.3.8, and you can go back and see what the statement of that is. And excuse me. Yeah, so in proving 1.3.8, you can look back at I have a solution as well on here. So given x and y, so these are going to be random variables going from a measure space omega into R. We assume y is measurable with respect to sigma x R. And remember, sigma x is just here, so I'll write it like this. So y is measurable in this sense, which I will talk about later. And after we assume that, we need to conclude there exists an f from R to R which is measurable such that y equals f of x. Now, let's see here. This is really just like half of 1.3.8. This is sort of like 1.3.8 is an if and only if statement, so you have to prove sort of two directions here. But this is the part of it that we're going to solve using this constructive argument. So also here R, which is not the real numbers. This is just sort of uppercase. So here, this is just like uppercase R rather than like boldface R. So uppercase R is the Borel sigma algebra on the real line R. Okay, so basically what we do is x, by definition, so basically this x inverse of R means that we basically, this is the collection of sets in omega, which are inverse images under x of Borel sets, or sets in the Borel sigma algebra in R. So sets in this uppercase cursive R. So by construction, by just definition, x is x inverse R to R measurable, because to be measurable means that the inverse image of the inverse image of a measurable set in your codomain is measurable in the domain. And so you just take all the inverse images under X of Borel sets in R, and that gives you a sigma algebra in omega. And so in this way you get a sigma algebra in omega with respect to which X is measurable. And then all we need from there is, so this X inverse R, as is talked about in the textbook, is referred to as sigma X, because it's a sigma algebra in omega, which is sort of not like generated by X, because typically when you talk about a sigma algebra being generated, you take a class of functions and you talk about a sigma algebra generated by a class of functions. No, you take a collection of sets and you talk about a sigma algebra generated by a collection of sets. Here, what we're doing is, because that definition only really applies to collections of sets, we call sigma x the sigma algebra generated by the function x. And then because we're talking about functions instead of sets, it's clear that we're talking about this different definition. So basically saying that a sigma algebra is generated by something, the definition will change depending on if that something is a function or a collection of sets. That's just a whole bunch of background. This isn't really super critical for the exercise. This is just background. Yeah. Okay, so now we assume that y is measurable in the same sense. And what we need to do is we need to find a function f from R to R which is measurable and such that y equals f of x. And so we do this in 1.3.8 using 1.3.7, which means, and 1.3.7 tells us that the collection of measurable functions. So here, I believe what it tells us is that the collection of measurable functions contains the collection of simple functions and is closed under pointwise limits. And we will certainly be using 1.3.7 in this argument as well. And so what we're sort of doing is, this is all sort of like, I guess, redundant in some sense, because we use 1.3.7 a lot in this argument. But it's still nice to have like a constructive proof, because I think that if something's a little more clear, then yeah, it makes more sense. Or if something's constructive, then it's easier to wrap your head around. At least that's what I personally find. And it is interesting that this, what we're dealing with here is, like, if you look at the set omega, which we're going to, omega such that y of omega is between m2 to the minus n and m plus 1 times 2 to the minus n. Basically, this construction is going to look a lot like the construction that's used in 1.3.7. Because in 1.3.7, part of what we did was we found that, like, if you take a measurable function, you could approximate it by simple functions. And the way that you construct these simple functions is sort of similar to this. So I guess in that sense, because these constructions are so similar, you're not getting a whole bunch of new information. But it is still nice. All right, that's enough rambling. I should probably actually solve this problem. Okay, so given n and m, these are going to be natural numbers. Set of omega such that m to the minus n is less than or equal to y of omega, which is less than or equal to m plus 1 to the minus n. So this is, by definition, y inverse of the set m to the minus n, m plus 1 to the minus n. All right, and now this is a set which is this m to the minus n comma m plus 1 to the minus n. This is a Borel set in R. And we're taking the inverse image under y. And so therefore, this resulting set must belong to the sigma algebra in the domain of y. And remember, the sigma algebra in the domain of y is x inverse r, because we assume that y is x inverse r comma r measurable. So this is an x inverse R. Okay. So what this means is that there is some BMN. So this is a set which is a measurable set on R, such that you take x inverse of BMN, and this is going to be equal to y inverse of m2 to the minus n, m plus 1 to the minus n. Okay, because remember, y inverse of this half-open interval is an element in x inverse R, which means it is the inverse image under x of some Borel set. Okay, so let's see here. Define Fn of x to be the sum over all integer values of m times 2 to the minus n times the indicator function on Bmn of x. So Fn is a function from R to R, and you plug in a real number, and if this real number belongs to, so basically, if you think about this, I guess one other thing that we should mention is that the sets, note that the collection BMN, where M ranges over all values in Z, is a partition of the real line R. Because basically what you do is you take the real line and you break it up into intervals of length 2 to the minus n. And then you just put these all next to each other. And because these form a partition of R, if you fix an n, then for any x in R, there is some m such that x is in Bmn. And so when we take this sum in the definition of the function Fn, this, for any fixed value of x, this sum will turn into, all of the terms will drop out except for the one term which corresponds to the Bmn to which x is an element. And then you just assign the value m times 2 to the minus n. All right. And what you can see here is this is simply the limit as k goes to infinity of the sum from m equals minus k to k, m to the minus n, indicator, the set Bmn x, okay, now this limit shows that that Fn is a pointwise limit of simple functions. Because for any particular x, you just choose k, x is going to be in Bmn, and so you just choose k larger than, so for any value of x, x will belong to some Bmn, and so long as k is larger than the absolute value of m, this function is going to evaluate to m2 to the minus n. And so this converges pointwise, and it converges pointwise for every point. And so Fn is a pointwise limit, and this is all the functions in here are simple functions. So the Fn is a pointwise limit of simple functions. So by 1.3.7, Fn is measurable because all simple functions are measurable, and measurable functions are closed under pointwise limits. All right. So, okay, so each Fn is a measurable function. And now we want the collection of functions Fn to converge pointwise. We know that these simple functions converge to Fn, but now we need the Fn, and the simple functions converge to Fn pointwise, and now we need the Fn's to converge to F pointwise. Okay. And this function to which it converges, we're going to call it F. So we want the Fn's to converge pointwise. So given an x value, and so I'm just going to specify here that this is going to be an x value in x of omega. Because if we look at Fn of x, basically the BMNs are all subsets of the image of x. And so we only need to define Fn, or Fn is only really defined on the image of capital X. So we're going to take a lowercase x in capital X of omega. So given this, now there exists some omega in capital Omega such that x is equal to x of omega. And that's like if no such omega existed, then x would not be in the image of omega under x. Okay, so now if we have n1 and n2 and n, and we'll assume without loss of generality that n1 is greater than or equal to n2. If n2 is the bigger one, you just flip the names. So given these, there must be some m1 and m2, also natural numbers, such that y of omega must be in m1 2 to the minus n1, m1 plus 1, 2 to the minus n1. Because again, the intervals of this, if you let this intervals of this form range over all values of m1, you're going to get a partition of R. And since y of omega is in R, there must be some value of m1 which will make this interval contain y of omega. But this is also true for m2, 2 to the minus n2, m2 plus 1, 2 to the minus n2, because this is also a partition. But you see, the first one is going to be a subset of the second one, because 2 to the minus n1 is going to be smaller than 2 to the minus n2. And so because of that, this half-open interval on the left is going to be contained in the half-open interval on the right. And I guess maybe if you wanted to, you could sort of argue that, or sort of state explicitly that these sets on the left are never... basically what this is going to look like is the larger sets are going to look like this, and the smaller sets might look like this. Well, I guess no, these are powers of 2, so we would need... So let's just say this for simplicity. So basically what's going to happen is these endpoints are going to line up. And you're never going to have a case where you have a half-open interval that's like this, where it's between two things. And I guess you could argue that if you want, but I think given the fact that the length of these intervals are 2 to a negative power and they all intersect, say at 0, you can conclude from that the endpoints are going to intersect. And so you don't have any of that overlapping that I was talking about. This set on the left will be entirely contained in the set on the right. Yeah, so I'm just going to leave it at that. Okay. So y of omega is in both of these sets. So f and I of x of omega, remember this is sum from m equals minus infinity to infinity, m2 to the minus ni, indicator function of b, m, and I of x of omega. And so this is going to be, this term is going to exist precisely when x of omega belongs to b, m, and I, in which case the resulting value is going to be b, or mi 2 to the minus ni. And this will hold for I equals to both 1 and 2. So basically, yeah, I'm just, instead of doing this for I equals 1 and 2 separately, it's the same argument. So I just do it for both. So what does this tell us? So, all right, come on. I know I'm getting sort of lengthy here, and so my computer's not liking that. So, the difference between fn1 of x of omega minus fn2 of x of omega, well, this is going to be m1 to the minus n1 minus m2 to the minus n2. All right. Now, this, remember the half-open interval, y of omega is in these two sets, and remember the one on the left is a subset of the one on the right. So m1 2 to the minus n1 is somewhere between m2 2 to the minus n2 and m2 plus 1 2 to the minus n2. So that means that their distance must be, or the distance between these 2 points can be at most the length of the interval m2 2 to the minus n2, comma, m2 plus 1 times 2 to the minus n2. And the length of that interval is, of course, 2 to the minus n2. All right. So, what does this tell us? So, if we're given any epsilon, or if you fix any point x in x of omega, so I guess I could do this like this if I wanted to. It doesn't really matter. I think I was making a bigger deal of x being an element of x of omega than I needed to. All right, if you choose any x in the image of omega under capital X, if you choose any x value, then choose n2, choose a natural number capital N such that 2 to the minus capital N is less than any given epsilon. Then, as long as n1 and n2 are bigger than this capital N, you're going to have f of n1x minus fn1x minus fn2x. The distance between these two values is going to be less than or equal to 2 to the minus capital N, which is less than epsilon. So what this tells us is that fn of x is a Cauchy sequence, which I suppose I could have said beforehand that this is where we were going with this. Like, to prove that fn converges pointwise, we are going to prove that fn of x is a Cauchy sequence. Maybe it would read better if I had said that before. Oh well. Anyways, this is a Cauchy sequence. And since it's an R, which is complete and everything, which converges to a value which we will call f of x. All right. So the resulting function f is a pointwise limit of measurable functions so again, by 1.3.7, it is measurable. All right. So we've got our function, f, and we've constructed it sort of constructively. I guess that's sort of a redundant way of phrasing it. This is somewhat of an explicit construction of f, even though it's just sort of a limit of functions. But anyways, now we need to finish off the proof, and this finishes with y equals f of x. So let omega be an omega, given natural number n, there exists an m, such that, okay, so again, we've done this before. So we choose m and n accordingly. So x of omega is in Bmn, and fn of x is going to be equal to m to the minus n. Again, same stuff we've done before. So then, the distance between fn of x of omega and y of omega is, well, it's going to be the distance between m to the minus n, and y of omega is somewhere in this half-open interval, which again we've talked about. This is less than or equal to 2 to the minus n. So, what this tells us is that 0 is the limit as n goes to infinity of fn of x of omega minus y of omega, and we can bring this limit inside the absolute value signs, fn x omega minus y of omega, and of course we know what this limit of the fn's is. This is just f of x of omega, this is what we just proved, minus y of omega. All right. So the distance between these two things is 0. So f of x of omega is equal to y of omega. And this holds for all omega and capital Omega. So f of x equals y. So there we go. Sort of a lengthier proof. Some redundancies. I don't know. I sort of like the previous solution because, like, if you think back again, if you think back to 1.3.7, the way that we proved that was we used a construction of a limit of simple functions, which are very similar to this. It uses those same sort of sets B, M, N. And so I don't really think we gain a lot of additional insight from this exercise above what insight we had before. But at the very least, it's good practice. Especially because this whole working with like measure spaces and stuff can be a little bit tricky. But anyways, yeah, that's all there is to this exercise, and so we're done.